do this on the same page, but solving that for v, not too bad. Subtract g and divide by rho. So subtract g, it's going to be a e to the negative rho t minus g over rho. And I'm just going to, again, divide each term, and I'm going to call that a different constant, a over rho. Just call that b for a second. E to the negative rho t minus g over rho. Okay. And again, just notating what that b is. B came from a over rho. Okay. Sometimes you look at this stuff and you want to have a meaning in the back of your head at every step. Okay? That's hard. Okay, so sometimes you gotta let it wash over you and trust that you know the math behind it, and we're gonna get to a final step where we solve for the velocity, and eventually, if this is the velocity at time t, I can integrate again to find the position, and that's what we're looking for. Okay, so that would be a function that gives us the position of this object, whether I throw it or throw it downward or drop it from a resting position, taking into account the wind resistance. So you can see from assuming no wind resistance to assuming linear, wind resistance is linear to the proportionally to the velocity, makes it a little bit more complicated. All right. Okay. Now, if we use our initial condition, well, we didn't really have one, but v of 0 is equal to what we're going to call v naught. So put in 0 for t, what do we get over there? Now, e to the 0 is just 1, so I'm going to get b minus g over p. Or not p, rho. Yeah, there we go. G over rho. That equals v naught. Okay. And what this does is it allows us, usually we'll know v naught. Who knows what v is? I'm going to just take this opportunity to solve that for that constant b. b would represent v naught plus g over rho. All right. Now putting that back into the velocity, b right there, we get velocity, and we have it explicitly in terms of t now. Replacing b with this guy, we get v naught plus g over rho, e to the negative rho t, minus g over rho. Okay. And I'm just going to call this equation 2 here. All right. So a couple things to note. Does this look like the velocity function of the velocity when we assume no wind resistance?
No.
No. This is exponential in t, right? And what happens? Well, yeah. Let's write down a couple things. So a couple notes. First, this is no longer linear with respect to time. Okay? Whereas velocity here, of course, is velocity, initial velocity minus gt. Its velocity is linear with respect to time. It speeds up linearly. Yeah? Okay. And of course, this velocity model assumes that as t goes to infinity, the velocity just becomes, well, if it's falling, the velocity goes to negative infinity, which means no bound for the speed of this object. Okay? So that is, we know not to be true. All right. So let's note that first, that the velocity is no longer linear. Okay. And what else do we notice? It is exponential. I got a negative factor up there, a negative exponent. So what can you tell me about the limit as t goes to infinity of this velocity function?
It's going to be slowing down. It's going to be moving towards zero. Right?
Right.
Well,
Where
it's
did
going to
we
be
change?
negative one.
The good thing about this
Terminal
equation is we don't
velocity.
have a ton of different parameters. Rho is the most complicated one. Rho was what? K over M. Both positive, right? So rho is positive. As t goes to positive infinity, we get e to the negative infinity, which is going to what? 0. And that's that, attached to that whole factor. That whole thing goes to 0. And we just get negative g over rho. So what does this mean?
There's some. Yeah.
Right, this is the limiting velocity. Okay, this is what we call terminal velocity. Okay, which we know an object will have. Now, that terminal velocity, it's not a fixed number, right? It depends on, well, of course, the force of gravity, but the mass of the object, as well as that constant k, which can take into account that constant k. There's actually a good discussion about it in this section in the book. Okay, I'm finding this book, some of the things they talk about, it reads pretty good. So they talk about that constant. It might have to do with the pressure of the atmosphere.
I'm assuming it also has something to do with the surface area that's getting hit.
Right, probably the surface area, the object that's falling. That could take a lot of things into account. Are you dropping a Nerf football or are you dropping a shot put? So it has to do with mass, of course. It also has to do with viscosity of the fluid in which the object is falling. Is it water? Is it air? And what's the density of the gas?
Is it peanut butter?
Is it falling in peanut butter? Is it falling in honey?
Kind of just, so one of the things a lot of physics classes do is they show that two objects fall at the same rate regardless of their mass. This implies that the mass does actually impact the terminal velocity, which is, well, the heavier objects fall faster once air resistance is taken into consideration, which is really interesting.
Yeah.
It's kind of,
Yeah.
drop two objects and they'll fall at the same rate until
That the mass does.
until they reach their terminal velocity. So.
Right. So if you dropped, in atmosphere, if you dropped a shot put versus a Nerf ball of the exact same size, it's pretty clear one's going to fall faster than the other.
At a certain point, they're going to accelerate at the same rate.
Drop like a shot put and then a little marble that's made of the same material as a shot put, and they should fall at the same
It
rate.
should.
But density?
No.
The cross-sectional area comes into
If they're the
play.
same density.
Same density, same mass.
It's surface area.
Well, no,
It can have
the
the
surface
same
area, the surface area
surface area.
should take into consideration the K, so that.
Yeah. So all this other stuff that you're thinking of, this is shoved into that constant K. Well, it depends. And they talk about it because, well, one, and I'll get to your question. But one assumption that we operated on was that wind resistance was proportional to the velocity that the object is falling. How reasonable is that? They also talk about that, well, maybe it's more reasonable to think that the wind resistance is proportional to the square of the velocity, which would affect it more. The faster it's falling, the wind resistance is proportional to the square of that velocity. Okay, they actually talk about that. They say in practice, that exponent is probably somewhere between 1 and 2, and you can take that k value between different ranges as well. So it depends on different things. Okay, so good discussion. All right, and what was your question?
I was going to ask if it was actually linear, or if it was some other, relationship.
Just in all probability, it's probably not exactly proportional to v to the first power. You know what I mean?
Somewhere close enough that this is a decent model.
Yeah.
And this is like, you were dropping shot puts off the top of the tower of Feely, right?
Mm-hmm. Yeah, I mean, if it was just random, it would be really it would be pretty amazing that it was exactly proportional to v to the first power. If it's some power, it's probably proportional to v to some random number between, some power.
E or something.
Who knows? Yeah. V to the e minus 1 power. I don't know. Anyway, so this takes into account things like that, and then we do get a terminal velocity. All right, now what we're going to do next? We got the velocity. Okay, a function that would model the velocity of this object at time t, and as t goes to infinity, we do get a constant. So it converges to a constant velocity. But we can also go ahead and find the position function. So if we integrate equation 2, that's velocity, and velocity is dx dt, right? So this is integrable, although kind of ugly. We got these constants to deal with, but so integrating 2 would give us position function. Okay, and that's what we're going to do here. All right. So y of t equals, I'm just going to put integral of this function, v of t dt, equals, all right. Now, I did this all this morning, and I'm just going to write down, all right, let's see. Okay, so we get this, now this is a big exponential term right here, right? Some constant out in front. But I also have, it's not just e to the t, it's e to some function of t. So we're going to get that back up to a constant multiple. So this is going to be g over rho, e to the negative rho t. But if I integrate this, I'm also multiplying the last step, the chain rule of a factor of negative rho would come out front. It needs to knock out with something so I don't get anything in front, and that is going to be its reciprocal, negative 1 over rho. Negative as well, because when it differentiates, it's got to give me this term back. So that negative rho is going to pop out, cancel with the negative 1 over rho, and give me that as a derivative. Okay? The good thing is this is a constant with respect to the variable t, so we just get minus g over rho t plus some constant. I'm not making any assumptions about this, that this is actually the initial height. Probably isn't. So I'm going to call it c. All right. What I'm going to do is use initial condition. Well, let's go to the next page. All right. So initial condition, just saying that, all right, so let's use at time 0. So initial height of this object, if we call that y sub 0, why not? Then we get, put in 0 for t. And what do we get when we put 0 in there for t? That gives me 1. I'm going to get negative 1 over rho, v naught plus g over rho. Put in 0 there, that just knocks out that whole term, plus c. That's equal to y naught. Okay. Now, the one thing I want to get rid of in this equation is c. So I'm just going to solve this equation for c, and we're going to set it back in. So this gives me c equals, I'm going to add this whole term over the other side. It's going to be y naught plus 1 over rho, v naught plus g over rho. Okay, now substitute that back into the equation. Right? For c, we get y of t equals negative 1 over rho, v naught plus g over rho, e to the negative rho t, minus g over rho t plus c, which we just solved, is this gigantic mess. I'm gonna rewrite this. Just put the 1 over rho term in front. V naught plus G over rho plus Y naught. So I'm gonna just leave that at the end. Now, that's ugly, and memorize this? No. Don't try that. Now, I mean, it's just a waste of space. But one thing I'll point out, the last algebraic step, is that we do have a giant common factor, well, at least these two terms, have a 1 over rho V naught plus G over rho. 1 over rho V naught plus G over rho. Yeah.
So, like, if you multiply the 1 over P out, you get the position plus velocity over rho plus gravity over rho squared. So it looks a lot like the.
It looks similar, yeah. You get
I mean, there's some relation.
some relation,
So
yeah.
It's not
Yeah.
completely
Although
bad.
this is not a polynomial. Yeah, it's not
Right.
polynomial anymore. It's not.
It's like an inverse polynomial.
Well, it's exponential with a linear piece.
Yeah, I don't know.
Yeah, it's not a pure exponential. It's not linear. All right. But what I'm going to do is I'm going to do a little crazy factoring here. There is a common 1 over rho V naught plus G over rho. Okay. So here's what I'm going to do. I'm going to factor it out of these two terms. I'm going to leave these two guys alone. I'm going to put this in front. I'm factoring out 1 over rho V naught plus G over rho. Okay, we're factoring that, so I pull that out of this term. I got 1 left when I kind of put that up front, factor that whole thing. I'm going to have 1 minus, pull that out, e to the negative rho t. Okay, we left these ones alone, so that's minus g over rho t plus y naught. Okay. Whew. Let's see if that's right. V naught plus 1 minus e to the negative rho t minus g over rho t plus y naught. Yes. So that is the function for position. Okay. This gives us the position at time t. Or height, whatever. It depends on, if it's forward and backward motion, horizontal, but, or up and down. I don't want to call it height, but this is just the position function, displacement. Okay? So, will you have to go through that? No. That derivation process. But just to show you that, yeah, things get a little bit more complicated when you take into account wind resistance. Even if you assume that the resistance, or the wind resistance is proportional to the velocity. Okay? One thing to notice, though, I'm just going to make one note about this equation. As t goes to infinity, what type of function does this approach? Yeah. This is a negative rho t. We already established that rho will be a positive constant, so this is negative overall. As t goes to infinity, this term is going to be approaching 0. So I'm just going to have, 1. So I have all of that. That's a constant. Minus g over rho t plus y naught. This approaches linear. In other words, this exponential part drops out. Basically, it becomes inconsequential, and it approaches a linear function. Why would that be?
Because the position, it's not getting any faster because it hit the maximum velocity.
Right. Right. You can argue that the instant that an object reaches terminal velocity, well, it's falling at a constant velocity. Therefore, its height becomes linear. It's falling at the same rate, so it's knocking off the same distance each second. So if you look at its graph, this part becomes inconsequential, and the height, if it's an object that's falling, the height becomes linear as it reaches a constant velocity. Right? Because the derivative of a constant velocity, derivative of that would be constant. That would mean that acceleration eventually becomes constant. Which makes sense. That's the instant when the wind resistance and the downward gravity negate each other. So it's falling at a constant rate, and its acceleration is constant. Actually, zero, right?
I was gonna say-
The velocity is constant, and the acceleration becomes zero. Yeah, right. It's off by one derivative. Okay, so yeah, you can have this formula. Never gonna ask you to memorize that. Okay?
Good test question.
All right, so any questions? I mean, the process is there, right? We just assumed something about the wind resistance proportional to velocity. We came up with a differential equation that models the velocity at time t, solve for v. So we got the equation for the velocity, and then integrate one more time to find the position. All right, and a lot of algebra. Okay, so any questions about that? Okay. Let's, well, I want to talk about one other thing in that section. There's some things that we're going to be disregarding, for instance. You can read it, it's good reading, like I said, but we'll disregard the case when the air resistance is proportional to the square of the velocity. But you can certainly read that. That gets it a little even more tricky. Because if it's proportional to the square of the velocity, well, the velocity squared is always positive. And so on the way up, you got to make sure that you get the right sign for that, the force of wind resistance. Because on the way up, wind resistance is acting downward, but v squared is always positive. On the way, when the object is coming down, v squared is always positive. So even when it's coming down, the square of the velocity is positive, but you want the wind resistance to be acting opposite of it, so you have to make that negative. So that constant changes signs depending on if the object is going up or coming down. You have to take those cases separately, consideration separately, because v squared is always positive, as opposed to when it's proportional to the velocity. When the object's going down, the velocity is negative, right? And so that negative knocks it out. When velocity is positive, then negative v is negative.
K essentially has to be a piecewise function.
It has to be a piecewise function for the position.
That's exactly what
The velocity.
Coach.
Yeah. All right. So we're going to disregard that, but it's good reading. It helps your overall understanding, I think, just to gloss over that. One thing I'm going to talk about briefly, because I do want to do some practice today instead of just lectures. Another of Newton's laws, say we have variable gravitation. Now on the surface, gravitation acceleration, ACC, I'm just going to abbreviate that. So variable gravitational acceleration. Okay. On the surface of the Earth, at 0 sea level, the force of gravity is nearly constant. Well, that's different if you go a mile up. Okay? It's different than that if you go 2 miles up. And eventually, when you escape the Earth's gravitational pull, well, you're going to be getting gravitation maybe from somewhere else. So it's variable. Okay? And if you talk about 2 large bodies, then the force, of gravity between them depends on a few different things. And of course, Newton came up with a law for that too. How? You know why Newton had all this time? Well, A, he was a misanthrope. He didn't deal with anybody else on a personal level usually. And B, when he discovered calculus and a lot of this stuff, anybody know why or when it happened?
He couldn't do a physics problem?
Right. Well, yeah, he wanted to solve physics problems, but
Campus was
he
closed
really,
for a while.
campus was closed. You know how we have our snow days, and it's pretty laughable. We have a snow day because we get a half an inch of snow.
Yeah.
They closed Cambridge or Oxford. Cambridge?
Yeah, Cambridge.
Wherever he was. They closed it for like 2 years because of the Black Plague. So that's a snow day right there. So he went back to his home, his farm, He hated other people, he didn't get along with people, so he went into his study and did all these experiments, came up with calculus, laws of gravitation, laws of optics, by poking his own eye with a stick and tweaking it and drawing what he saw. Anyway,
He also,
so Newton did that.
he was also disappointed at the end of his life because he really put all of his time into alchemy, and he felt like he was a failure at the end of his life because he didn't solve alchemy's problems.
Yeah, he was a weird guy. He was a mason, and he was an alchemist in his spare time.
No, in his spare time, he
Would
did
not
not
be able
physics.
to
Yeah.
Didn't like Einstein like his theory of
I
relativity?
was watching an interesting thing on OPB on him and Hook, you know, and
Oh,
the
yeah.
battles that Newton had with other people. He had a battle with Hook, and that's why he didn't publish a lot of his stuff, because of this early, this early sort of disappointment he had about this battle over his stuff, precedence, who did it first. So he came up with calculus and sat on it for a while until he saw Leibniz doing it, and he said, hey, I already figured that out. You got your hands on my stuff. So he didn't publish it, he sat on it, and then accused other people of stealing it.
Nice.
What a great guy.
Einstein, you just stole
Yeah, I like Leibniz notation is much better. If you look at the, and I haven't read it, but if you look at some of the original stuff, Newton's notation is not used at all. Yeah, he had some weird stuff, fluxions and fluents, and he used a system of dots that look like umlauts and.
Oh, dot notation is his fault?
What's
I wanna
that?
go back
It's
in
used a
time.
little bit, just like, not by mathematicians ever.
Right. Yeah, that sort of thing. But this is the other one, law of universal gravitation, I think it's called.
Yes.
It talks about the force of gravity between two bodies having mass big M and little m, so two objects. So this describes the force F between two objects or bodies. And I don't know, a lot of you probably, much more on top of this than I am. Two objects with masses big M and little m, and distance r between them.
Between their centers and mass.
Right, yes. Centers of mass, is that the same thing as centers of gravity? Yeah.
Maybe.
I don't know. I forgot about all this stuff. All right. So G is some sort of empirical constant that, I don't know. Put all the stuff that's unknown, put that into the constant G. All right. Big M is the mass of the first object. And little m is the mass of the other object. And yeah, r is the distance between them. And technically, yeah, they're centers of mass or centers of gravity. So if it was an object with the Earth, it would be the distance from probably the center of the Earth. Okay.
Yeah, and these, they take it to be like a point,
Right, a point, yeah.
like technically the very inner, like if all of it was combined to something.
At the center of the Earth with, point, but having mass at the center of the entire Earth. Yeah. So, and this doesn't have to be the Earth and anything else. It could be any two, celestial bodies, the moon and the Earth. A small object, in the center of the Earth, right? Its gravitational force is minuscule compared to that of the Earth.